Hello. Well, we're just about there. Welcome back, everyone. Okay, it looks like we can start. Well, we're about to finish off week 6, but this is pretty much what the class is going to look like every Thursday. Quiz 4 is due today, and the new quiz is also posted, quiz number 5. Quiz number 5 is going to be about the product rule, a quotient rule problem, and then a chain rule problem. And that's pretty much our goal for today. We're going to finish off the Unit 3, Section 3.4 notes. One of my classes goes by units, so I've been getting sections and units mixed up. So we're going to finish off the 3.4 notes, reviewing the product rule and quotient rule. Then we'll move into the chain rule to finish off the day. We're probably only going to complete this section entirely when we come back next Tuesday, but that's what we have going on so far. Well, any questions at all, folks, to start us off today? Okay, well, let's jump in. Here's where we left off. We have a pretty gnarly looking quotient rule that we want to take a look into for our very next problem. But I honestly think that this would be kind of a rude problem to start off class right away with. Let's do a warm-up problem, just reviewing how the product rule goes, the quotient rule goes, and then we'll launch into this tougher problem right here. So let's hide that just for the moment. And we'll call this just say warm-up. For the instructions, we'll differentiate the following functions. And let's give this 2 parts. For part A, we'll look into the product rule for our first warm-up problem. Let's say for the product rule, where we're going to do, it's going to be a f of x equals square root x times e to the power of x, which would be a pretty standard kind of product rule type of problems that you'll see in the WebAssign homework. Before we even get started, if you're going to differentiate something like this, a great strategy is just write down the product rule on paper. So writing the product rule in its most simplest way would look like this. Here I'm just writing the functions, not writing out f of x or g of x, just the function names themselves, f and g. If you differentiate f times g, you get the derivative of f, copy g, plus copy g and multiply that by, or hang on, I got that backwards, plus copy f, start over a little bit fresh on that, and then multiply by the derivative of g. So sorry for backtracking on that one out of nowhere. Let's see, so that's close, except we have to hit this one with the product rule, but that's the right derivative for the root x and the right derivative for e to the x. It'll come in 2 terms altogether when we go to differentiate this one. And that's what's kind of tricky about the product rule. If it was something like, say, y equals 3e to the x, that problem goes a little bit faster. Here you'd use a constant multiple rule, and you'd say y prime would be just 3 because it's a constant multiplying times e to the x, and then our work would be done right there. But if it's a function that depends on x, multiplying another function that depends on x, now we have to break it down into 2 terms altogether, running through this product rule. So here's what the organization would look like. To really get this down pat, we have to say which function is which. Even though I've used the name f and g when I wrote out the product rule, it's more about first function multiplying the second function that we're differentiating. So our first function will be the square root of x. Our second function will be e to the x. And now we can say, if we take the derivative of f at x, through the product rule structure we see right here, our results will go in this kind of way. So I'll put in a placeholder for the f prime, a placeholder for g, then plus, and then another placeholder for f. And then finally, a placeholder for our g prime. Then we take the functions, square root of x being the first function. They'll go into these first placeholders that we put out. And then the second function, e to the x, will go into the remaining positions. So that's our start so far. And like Haley said, the derivative of this first one is really just 1/2 times x to the power negative 1/2. Let's put that out as, say, a separate problem altogether. For differentiating square root of x, you can rewrite this as x power 1/2, you're differentiating. That 1/2 moves down as a coefficient. New power on x is 1 less, so negative 1/2. There's lots of different ways to write that down, but this will always do just fine. So on our next step, f prime of x is going to turn into the derivative of square root x. We worked it out on paper here, so we're just dropping down 1/2 times x power negative 1/2. So that's this prime right here that we just worked out. Then we can just copy down the g function, e to the x, so multiply it. Plus, this says to copy down the f function. Here it is, we're not doing anything with it, just copying it down. But then it gets multiplied by the derivative of e to the x. That's this g prime part right here. That one's nice. The derivative of e to the x is itself as an e to the x. And then, depending on how much steps you want to take on this one, this would be a great stopping point. You could factor out the e to the x like we mentioned on the other problems. Let's take that extra step just to convey that's totally fine to do. F prime of x, if you decide to go one step further and factor, would be e to the x times 1/2 x power negative 1/2 plus the square root of x. Well, let's just emphasize, like we did before in the notes, both answers are acceptable. So that's our warm up for the product rule so far. Any questions whatsoever, folks, running through those steps? Okay, again, our ultimate goal to start off class is to differentiate that thing down there, but it's actually a bit of a monster, so that's not a good one to start class with. So let's do our second warm-up problem. We warmed up with seeing how the product rule goes, that formula here by the red dot. Now, if we're going to do a quotient rule, here's a pretty standard looking quotient rule type of problem. So for part B, I don't know why I wrote an equality right there. Part B equals is what I was thinking, but let's format it a little bit nicer. Part B is going to be the function g of x. Let's write this as e to the x over x squared minus 4x. So that'd be a pretty typical, I would say, routine exam 2 type of problem for part B as far as the quotient rule goes. The same with part A. That'd be a pretty routine kind of exam question as well for exam 2. First thing we're going to do is, if you're imagining you are taking exam 2, I'll be posting as we get closer and closer to the exam week, the page of notes that are included. And this is one thing that I'm going to put on the set of formulas for exam 2. This has pretty much all of the rules that we've been discussing to date. Not the chain rule, but we're getting there in the next section. I would look up this, put it down on paper, and just follow the structure. So let's do exactly that. Let's imagine we're doing this as an exam question. There'll be plenty of time, so we're taking care with this. There's a quotient here, so if we write down the quotient rule, that's a great way to get started. And this is a way to write it down just in a compact way. Again, suppressing the f of x and g of x, I'm just writing f divided by g. Then in this format, structure of the quotient rule goes f prime times g minus f times g prime divided by g squared. So that's the whole structure. It looks almost identical to what we put up here. You really only take 2 derivatives when you go to write out the quotient rule, the f prime and the g prime. And the biggest thing we have to do to tell the difference between is In product rule, you have the plus sign. And in quotient rule, you'll have the negative sign to work through. Okay, that gets us started. Next thing we'll do is organize. We'll think of e to the x as the function that goes on top. X squared minus 4x is the function that goes on bottom. And as we go to write this out, go g prime of x equals, here's us organizing further. There's 4 spots in the numerator, so let's put in 4 placeholders. And there's 1 spot to put information in the denominator. It'll be raised to power 2. So there it is. That is the entire quotient rule, written as just a structure where you slot in the things that you're working on. So the first function, the one in the numerator, is e to the x. Then it goes in those first positions, both here and here. And notice we're pretty much following the strategy we used for the product rule. Only difference is the change in signs and the fact we have a denominator. So there's 3 more spots to fill in, but the beauty of this is if you get the numerator position in those right positions, everywhere else, you just put in the denominator portion, x squared minus 4x. So it goes here, here, and finally here. So now we're ready to begin. There's just 2 last derivatives we have to take. Then we'll simplify it as much as what seems appropriate and feasible to the problem, and we'll be done with this one. Well, any questions at the moment, folks? Just getting to this step. Okay, let's move forward on the next steps with this one. Again, our goal is to do part C, but I think these warm-up problems are a great way to start off class today. On the next line, g prime of x is going to be equal to, take the derivative of e to the x. No change. That's the world's nicest derivative, making it sometimes slightly tricky because nothing happens when we differentiate it. Copy x squared minus 4x. Minus, here, copy e to the x. Then over here, we're differentiating. The result is going to have 2 terms. So the critical step is we have to make sure we associate those 2 terms. E to the x multiplies through. But the derivative is not too bad. This one's just a degree 2 polynomial. You'll get a 2x from this term. If it's x power 1, all you'll get is a coefficient, -4. So that finalizes all the derivatives. We're dividing by x squared minus 4x to power 2. Last thing we're doing is just simplifying it. Let's see, can this simplify in any kind of way? Yeah, it might simplify just a little bit. I do see some like terms there, that -4x and the positive 2x. But a really great way to simplify this one is to not distribute the e to the x in. This one's much better if we just factor e to the x out and then combine our like terms. Makes it easier on the eyes as well. So here's how I would simplify this one. E to the x appears in 2 positions. So you could just factor it out. It's the greatest common factor now. If you factor that out, what's left behind is x squared minus 4x from this spot. You can drop parentheses there because it was only needed because it was being multiplied by e to the x. E to the x drops out of this term, but now we do need parentheses because the negative sign will distribute in. Divide by x squared minus 4x power 2. So I need to distribute in that negative sign, then we'll combine like terms and be done with this derivative. So I have e to the x squared minus 4x, minus 2x plus 4, all over x squared minus 4x squared. And last step is just to combine the -4x, -2x. So the end result for g prime of x on this one is we've got an e to the x times x squared minus 6x plus 4 divided by x squared minus 4x to the power 2. This one was actually kind of tricky. There's lots going on here. But let's say you're doing this as an exam question. In an exam setting, if you get to just this step, say right here, that's probably quite a lot of partial credit already. In a 5-point problem, I would say that it's worth 2 points partial credit just getting the structure right. If you make a mistake here, you might lose a point, but take your 2 derivatives, that's the rest of the credit, getting down to here, and simplifying for the final point. So I'd say to that step is 2 points. To this step, just taking those 2 derivatives, this would be the other 2 points in a 5-point problem, imagining it's 5 points total. So in an exam setting, if this is a 5-point problem, this is about how we'd be grading each one of these. We get 2 points here, do a sensible thing to simplify it down, and it would be 1 point for the end answer after simplifying. Well, that's our complete warm-up. That took about 16 minutes so far, but any questions at the moment? Okay, I'd say the biggest takeaway with these 2 warm-up problems is there really is a lot going on. We write down the quotient rule and even the product rule. If you just go in stages, think about what the structure looks like, slot everything in, go step by step, taking the derivatives. It's just one of those things that's more like a process, kind of like a cookbook recipe that you do in stages, and you'll eventually get to the right answer. So practice the problems on WebAssign. The quiz number 5 that's assigned is going to be problems like this as well. And you'll get a really good feel for how these are going to go in a real exam. So now we're on the level of this one. So in WebAssign, there's lots of routine problems that make great exam questions. But occasionally in the homework, there's a couple questions that are just a little bit harder. And this is one of them. I wouldn't assign this one on an exam because it kind of just goes a little bit too carried away for a good exam problem. But if you want to get great at doing the problems on exams, sometimes we do have to do harder problems like these ones, this one right here. So even though it's not a great exam question, it's a fantastic question for just practicing all of our results, all of our differentiation formulas, all in one shot. So let's give this a try. The challenge with this one is we see a fraction, so we're thinking quotient rule, but that's not the whole story with this one. Every differentiation formula we put down on paper can intersect with each other, can be used at the same time. This one's both the quotient rule, and from right here in the denominator, it's also a product rule. So this is one of the problems where we'd want to do really, really carefully in stages. Let's first think in terms of numerator versus denominator. Just write out what is the quotient rule on this thing to begin with. G prime at x goes derivative here, copy a function here, minus, copy a function here, put a derivative there, and then divide by something to power 2. So if we get that on paper, that's the massive, huge step on the quotient rule. Now we organize further by slotting the functions in the right positions. X e to the x goes here, x plus e to the x rather. We differentiate it, it goes here, where it's just going to be copied down in the next step. Then same song and dance, but different function. We're going to use the one in the denominator. It goes in all 3 remaining positions. 1 minus x e to the x, 1 minus x e to the x, 1 minus x e to the x here. And now we're on our way. Now this derivative is not so bad. If you differentiate x plus e to the x, you get a 1 for the derivative of this term plus e to the x. So that one's kind of a routine, nicer derivative. But this one, it's challenging just on its own as a problem. 1 minus e to the x prime has the derivative of a constant rule, the difference rule, like going along with the sum and difference rule. And right here, it's a product rule all in one. So there's 3 differentiation formulas on that one. Our goal is to kind of train our eyes to see when do the rules come up, how to navigate through the rules in an efficient way. So even if it gets kind of convoluted and a little bit overwhelming with all the stuff here, if we just focus on this one spot, get that derivative in, we can substitute it back in and be on our way with this one. So here's a good strategy where if things get more involved like this derivative, just break the problem in two. This is now the divide and conquer strategy that we're using. Let's treat y equals 1 minus x e to the x as its just own problem. If we could differentiate that, we'll put the result right up here. So let's work through this derivative. Y prime first would be differentiating the constant. That goes to 0 because it's not multiplying anything. There's no x variable there. So I'll put 0 just as a way to convey we took care of that, that derivative is done. But often we wouldn't write anything at all. The constant will just vanish. Next, we're differentiating this whole thing right here, including the negative sign. So I'll go plus the derivative of negative x e to the x and differentiate like that. There's other strategies you could take. If you preferred, you could have said, let's write it out this way, or y prime is going to be equal to 0 minus x e to the x prime. You could work it this way as well. I kept the negative sign on the inside because I think it's easier to see the product rule this way. But if you kept the negative sign on the outside, that would work just the same. Your product rule would be in the inside, and you'd have to distribute the negative into that whole result. Same strategy, just a different way of starting it out. So I'll do it in this way because, again, I think it's just easier to see the product rule in that particular format. But any questions to this step so far? Okay, so we started by writing down the quotient rule. Well, then this level, here we're using product rule. Out of nowhere, the rules are kind of interlacing with each other. But if it's a product rule, we can do it just as we've done all the others. This would be the first factor, the negative x function. Second factor is the e to the x function. And so now y prime will be equal to, we've wiped out the constant. Now for the structure, this will go the derivative of the first function, copy the second, plus, because it's a product rule, copy the first function, multiply by the derivative of the second function. Now slot in those functions. We'll have a negative x here, here, then an e to the x here, and here. So same kind of steps that we took up here in the quotient rule, but now it's no denominator and a plus in the middle. So now when we work through these steps, we take the derivative of a negative x, that comes out as a -1 altogether. I'll just write it as a negative sign. It'll be negative of e to the x. If you wrote -1 times e to the x, that's fine too, but it simplifies to just negative e to the x overall. Then plus, here we're copying this one, so plus a minus x. Probably a better way to say that is just going to be minus x. Derivative here of e to the x is just itself. And that's the whole result. So we survived a product rule, but now we have to inject it back onto the top here where we were working the quotient rule. That's okay. We're just going to make a substitution and then return to the original problem, g prime at x. So that's the divide and conquer strategy so far. Any questions at all, folks, getting through that? Okay, let's drop this in. We have g prime at x equals, while we're at it, we might as well differentiate this term right here. That's still one last derivative hanging. This one wasn't so bad. We use the sum rule. Differentiate x on its own, we get just a 1, plus derivative of e to the x is itself. Then, now we're on the level where we're copying things. Multiply by 1 minus x e to the x minus Copy x plus e to the x. And here, this was another product rule. It's a bit of a mess, but we sorted it all out. We'll substitute in the negative e to the x minus x e to the x into that spot. Then whole entire thing is divided by, I'm copying this part right now, 1 minus x, e to the x squared. So that one is already kind of an adventure. And again, I feel like this one goes a little bit beyond what a good exam question could be because there's just so much stuff for one single problem. This is like two problems duct taped together in one function, g of x. But I think there's one or two problems in the homework that's about this level of challenge. So we're doing some on the homework just to help out with the homework. Or excuse me, we're doing some in the lecture notes just to help out with the homework. We still want to simplify this thing, so let's go on to the next steps. As far as it simplifies, we're just wondering if there are like terms. Sometimes a good strategy is to try to factor something out, but it doesn't look like factoring is going to help on this one. Looks like we should expand and then combine like terms in the numerator to simplify this one. So here's the whole algebra process on this. Let's work out the distributions carefully. Multiply here to here, and we'll get a 1. Here to here in the FOIL process will give us a minus x e to the x. Next, distribute the e to the x inside, so this will be plus e to the x. And last, multiply here, using the idea we saw last class where e to the x times e to the x by laws of exponents gives us e to the 2x. We'll get altogether minus x e to the power 2x. Okay, that gets us started on this one. And here, we have to be careful because we're also not just foiling, we also have to distribute in the negative sign into the result. Some people might do this, and this is a great strategy. This is really just a constant -1. It can multiply into this group, or it can multiply into this group. And if you did that, this is what it would look like on paper. It would go plus here, plus here, plus here. It's a little bit easier to work through. I think that's a confusing step to leave on the lecture notes, though. So I'm going to do it step by step by distributing that negative sign last. But if you like that shorthand, that's a great way to do this kind of problem here. But doing it carefully step by step, this is what it's going to look like. Multiply x to negative e to the x. That'll just be a minus x e to the x. Multiplying here to here, we can combine the powers of x. This is going to be minus x squared e to the x. Then we reset, distribute e to the x on the inside. This will be minus e to the 2x on that multiplication. And final one, minus x e to the 2x. I honestly think that the algebra sometimes is more challenging than the calculus in a certain sense. And this is one of those kind of problems where we're getting a lot of good practice just on algebra itself getting through this one. The denominator is 1 minus x e to the x squared. And my next step will be to distribute this negative sign all on the inside. So if we do that distribution, I'll be copying up to this line, 1 minus x e to the x plus e to the x minus x e to the 2x. It takes a lot of oxygen to say all that. Now the distributive law will give us, let's just flipping all the signs to positive. So plus x e to the x plus x squared e to the x plus e power 2x plus x e power 2x. All divided by 1 minus x e to the power x squared. So there's its fully expanded form. And our reward for getting through all this is there's hopefully like terms. If there isn't, then that's kind of unfortunate, doing all that work for nothing. But we do have a minus x e to the x and a positive x e to the x. So those two terms cancel as pairs. And what else do we have? We have a x e to the 2x with a negative sign and a positive sign here and here. So these also cancel. Then there's a constant term, but that's the only one. Only one term with e power of x. This one and this one are unlike terms because the exponents are different. And this one's an unlike term because it has x squared on it. So those are the only survivors. All we're going to get left over is 1 plus e to the x all the way down to plus x squared e to the x plus e to the 2x, divide by 1 minus x, e to the x squared. So we did it, folks. This is the derivative of that original function g to the x, which is way up here now. And this is like the worst case scenario for as far as the derivatives would be for a homework problem. Haley says, feels like solving for a limit. Yeah, I agree. When we did the definition of derivative from scratch, the algebra got just like this. And that's also kind of an impressive thought as well. If we had to do this one from scratch using limits with the definition of the derivative, this would be just a huge explosion of algebra. That'd be a tough problem to get through. Definitely not. Yeah, I would say, Emma, for this one goes beyond what we would ever put on an exam situation. So this one's more like a practice problem, solving a slightly harder problem for the purpose of just seeing how these problems work together. There is, I think, 1 or 2 problems about like this in the homework, but not in an exam setting. This would be definitely going a little too carried away. Other questions so far? Okay, the big takeaway again is when it comes to all of our differentiation formulas, they really work together. We're going to see that happen in the next section, the chain rule as well. But this one was one of those problems, again, that is a pretty large one, not appropriate for exams. But once you master doing these kinds of problems, it's great practice on just getting good skills on all of our differentiation techniques so far. And also note, right on this line where the red dot is, that's the end of the calculus. Everything after that is just algebra down below. So if you feel pretty good about getting to that step, I'd say you're doing fantastic with these problems so far. If this looked pretty tedious, well, it was tedious, to be completely honest. We'll practice more stuff like this throughout the course. With what we're doing next in the notes, we're pretty much done with our topics, but we'll do 2 more problems. This problem is just, again, focusing on the structure of the quotient rule on part A, the structure of the product rule in part B, in a slightly different kind of scenario. Then we'll do an applied problem. This one is more for engineering. Looks like more electrical engineering if we're talking about power and battery that a laptop depends on. But this will be our next stop. We'll practice this, just another take at product rule quotient rule before we look into the applied problem. And again, this is a pretty nice roundup of just the formulas we have so far. This is the one that tells us the derivative of a constant is 0. This one is telling us the derivative of a constant multiplying a function is just the constant. It does not go to 0, multiplying the derivative of the function. Another great stuff. We've got the power rule, derivative of the exponent, the sum rule, the difference rule. But the major ones we're focusing on is product rule here and quotient rule here. And the problem is a little bit different as well. We're not just calculating f divided by g prime at x. We're also evaluating the derivative at a particular number, 3, and 3 here as well. This one is also similar to one you're going to see in the homework set. So if you're doing the homework in 3.4 and you see a weird one like this is a good spot to come back to on the notes. To start this off, we can just rewrite that if we're doing f over g prime at a number, here's what that process is going to look like. Whether there's a number present or not, that's the shorthand for the entire quotient rule. So this is going to be f prime at 3 times g at 3 plus f at 3 times g prime at 3 divided by the function g at 3 squared. So that's our quotient rule in action. We didn't do anything different from before. In essence, we put the derivative here. We have the function value here. We have the function value g here, but this one is the derivative. So same kind of idea before, and the function value in the denominator. What makes it tricky still on this line, though, is notice the information. We have to be really mindful of when we're gathering a function value, f at 3, versus when we're gaining the derivative of f at 3. So let's be careful on which ones we grab. We'll start with the derivative of f at 3. So that means we have to use this output here. So a 2 goes in first. Then g of 3 is an ordinary function value, so we'll grab the 5. And I'm noticing a mistake on here before I get too far. Anyone happen to see what the mistake is that I wrote on the step in the middle? It's one of those unfortunate mistakes that I try to avoid, but it snuck through this time. Anyone see what it is? Yeah, good call, Trayson and Emma. There has to be minus for the quotient rule. Good eye. So let's highlight that. That's always kind of an unfortunate error to make. And if this was a real exam question, I wouldn't like dock a whole bunch of points. That might be like -1 out of 5 points, but not the funnest point to lose. So don't forget, plus for the product rule, minus for the quotient rule. So good eye on that, folks. Let's backtrack and put in minus right here. Okay, with that distraction out of the way, sorry about that. Sometimes it is a good skill to find the error, but that was a kind of an impromptu find an error kind of problem. Next, we'll put in the function value f of 3, which is a -4. Maybe even before that, let me not forget to copy the sign. Okay, there it is. Now put in the function value, f at 3 is a -4. Multiply by the derivative for g at 3, so -4 again. Then we're dividing by something squared. Quotient rule says take g at 3, so we're just going to square 5 for our denominator. And there it is with that tricky negative sign duplicated correctly over here. All it is an order of operations problem now. We have 10 minus 16 in the numerator divided by 25. So this becomes -6 25ths altogether. Again, it's meant to be kind of a fast problem, but it can be tricky. So if you're getting values wrong when you try this out in WebAssign, could be something like this. It should be a minus sign there, and I put in plus. Or it could be just accidentally putting in this denominator, a -4, instead of the true function value, the +5. Well, that's one down. I know kind of the nice thing about these rules is if you've done one of them, you've practically done the other. So if you've done the quotient rule, the product rule is going to use the same values in the numerator. The only difference is the sign is plus in the middle. Well, let's write it out from scratch just to show how it goes. Following the product rule on this one, we'll get f prime at 3 times g at 3 plus for product, then go f at 3 times g prime at 3. So we have our f prime there, our f there, the function value g there, and the function g prime here. But it's the same exact information that we slotted in from before. So we'll get 2 times 5, just like before. We flip the sign to plus in the middle. Then we'll put in -4 times a -4. And that's the only difference if we're looking into the numerator portion, going from quotient rule to product rule. Flip the sign in the middle, same exact values. That means this one's just about done. We get 10 plus 16 for our overall 26 to end the problem. But we did it, folks. That's our pretty much last big look into the quotient rule, aside for the application problem down below. Any questions at all getting through this one? Okay, so we now have lots of fancy derivatives under our belt that we can use in a whole bunch of different kinds of situations, whether it's finding a tangent line equation, we're working in an applied situation, all these rules can now work together to help us differentiate stuff like this. But this is tricky. This is usually the big challenge in calculus. Once you see how the differentiation formulas go, it's one thing to differentiate without context, but when there is context, everything feels a little bit more challenging. So these are going to be problems we come back to in a big way in chapter 4. So it doesn't feel like just a sudden shock that we are dealing with these. We've been trying to differentiate stuff like this all along through the course as it comes up. So here's what the context looks like. It says the power that a battery supplies to an apparatus, such as a laptop, depends on the internal resistance of the battery. So that's just the overall context on what we're working in. It tells us next, for a battery of voltage V, internal resistance, R in ohms, the total power delivered, let's say to your laptop, that has resistance uppercase R is this. So this is the resistance of the battery. This is the internal resistance. Oh, that's the internal resistance of the battery is lowercase r. And the device has itself a resistance, uppercase R. So this is a nice real formula in this context of electrical engineering. This is the power being supplied to your battery. Numerator is the battery's voltage squared multiplied by the resistance of your, say, laptop. And notice the denominator is the resistance of the laptop plus the internal resistance of the battery, lowercase r, to power 2. So it's kind of a curious formula. What we want to do is calculate dPdr. That's just another way to say the derivative. So when you see dPdr, we're just talking about p prime. But we need to be specific. Here's where Leibniz notation really helps out. There are 3 variables here, v, r, and lowercase r. So we write out this way, what it's also telling us is v, lowercase r, are constant. The actual variable of our derivative is uppercase R, so it plays a role like X in the problems that we were just dealing with. And they reiterate right here, assuming that the voltage is constant, the internal resistance of your laptop battery is constant. That'd be bad if they weren't. There's something unstable going on. We're going to calculate the derivative, the rate of change of power, and then give the practical interpretation using the context. First thing to note is it's a quotient rule problem, because if we're calculating dPdr, r is the variable, and it's in the numerator and denominator at the same time, making this a bona fide quotient rule problem. So the major thing to look into is, what is the variable? It's that r up and below. Armed with that knowledge, we can say the rate of change of power with respect to resistance, uppercase R, is going to be this quantity. So let's put in just the structure for the quotient rule. Here, my color coding is more about what is the variable, treating everything else a constant, because that's the hardest thing about this kind of problem. Denominator is going to be something power 2. So that's the setup so far. Now we take the numerator, v squared r. It goes into these same 2 positions like we've been doing each time the quotient rule came up. So both here and here. Here we need to take a derivative, but it's a tricky derivative because it just doesn't look like anything we've done so far, thanks to a variable being uppercase r, playing the role of x, and v squared playing the role of a constant. Next, everything else is going to form where is going to go for where the denominator is. I said that so word salad, sorry. Every other placeholder will be filled in from what the denominator was. That's a better way to say it. So r plus r Power 2 will go here. R plus R. I need an extra set of parentheses, and power 2 will go here, and then we'll differentiate it. And then we have another set of parentheses on this one, R plus R, power 2 in the denominator, and we'll just square that. So that's the quotient rule so far. But because this derivative is tricky, we're going to go through this in really careful stages. First, working out this derivative here. Well, any questions at the moment, folks? Just putting it together with the quotient rule. Okay, so now let's work on this one right here. These have a way of being very tricky, like we mentioned, when the variables are no longer y's and x's, or f of x's and x's. So a great way to think about this is in terms of a fast analogy. Suppose you had a nice function, y equals, maybe it's something like 5 squared times x that you want to differentiate. The derivative of this one wouldn't be too bad. 5 squared is just 25, so there's nothing fancy going on there. The constant multiple rule then takes over. Y prime, when we differentiate it in terms of the variable x, would just be 5 squared. Or again, just a 25, but I'm writing it as a 5 squared to make it look similar to the v squared. Naomi says, will we not also have to use a product rule because of v squared and r squared, or are they not differentiable on their own? It turns out we don't need the product rule in this one, and it's all because v happens to be a constant, so we're just kind of in luck with this one. It's kind of like what we did right here. Because 5 squared is also a constant, the derivative of 5 squared times x didn't need the product rule. It would just be 5 squared altogether. Well, that's the analogy. Now we're going to do the derivative of this right here. But any questions so far first on just doing this part? Okay, again, these are really tricky kind of problems to see. But the assumptions that they made at the start of the problem are what's getting us through it. And in fact, when they told us to calculate dpdr, that was an automatic assumption that the only variable was r itself, and everything else, v squared and lowercase r, are automatically constant with regards to that derivative there. So if you take this and think in terms of that's just a 5 squared x and the derivative is 5 squared, then we can rewrite this example. It means if you have a function, say y equals b squared r, but you calculate the derivative of y with respect to uppercase R, I wrote it this way just to emphasize r as the variable. You could have called it just y prime. It's really the same idea as up above. If the variable is r and the exponent is 1, that's really r power 1. And at the same time, that's a constant, much like the 5 squared. This derivative is nothing but v squared altogether. So the variable r power 1 vanishes, just like the variable x to power 1. So all that happens in this derivative right here by the red dot is we get the constant, v squared. That's tough to see when we're first looking at this. We're trying to train our eyes to know which one's the variable, which one's the constant, to see what we get. Whether these are x's, t's, or Greek letters like theta, phi, or uppercase letters like r, the process is always the same for the constant multiple rule. Any questions at all, folks, for getting a v squared on this one? Okay, that's one derivative down, but notice there's still one more derivative to get through. So let's work out that next part carefully as well. Let me fix my penmanship a little bit on this one too, just to make it easier to read. Okay, so we're differentiating uppercase R plus R squared. Here's a differentiation portion right there. This derivative is a little bit unusual to take because of the power 2. What we want to do is, it really is a product rule problem because you could write it as R plus R times R plus R. Now it's a product rule. But if you just expand out that whole thing, it's no longer a product rule. It's just a polynomial in the variable uppercase R, and that's way easier to handle. So let's take the approach of just expand this one out. We'll see a different way to do it when we have the chain rule in the next section. But for the moment, this would be the official way to work this out. Take R plus R to power 2, which is R plus lowercase r times R plus lowercase r. We expand this out, we get R squared plus 2 copies of R plus times lowercase r plus lowercase r squared. So the full expansion would give us that after combining the terms in the middle. So that's the thing we want to differentiate. But it's a challenging derivative too. So let's take the strategy of working by analogy. Let's suppose we had a nice function. Y equals something like, say, 5x squared plus 5. We have a 2 there. Well, let's just go with a 5x plus maybe a 5 squared on this one for the part R squared. If we were to differentiate this whole function, it's really not too bad. These are the problems we were practicing in section 3.3. Y prime would be, first the power 2 would multiply the 5, and we would just get 10 times x to power 1 less, now power 1. Here, this would give us just 5 altogether. The power of x is 1, it multiplies the 5, giving us a 5. New power of x goes to 0, so now it vanishes by exponent laws. And that's just a constant. It's 25, so the derivative of whether we write it as 25 or 5 squared goes to 0, and our work is done on that one. So that's how it would go by analogy. But now imagining you're differentiating y equals r squared plus, let me reorganize this and rewrite it as 2r times uppercase R. I think that's a better way to see it, plus r squared. So if we're differentiating this, the variable is now r itself. It's playing the role of the x squared. So when we see the 2r right here, recall lowercase r is constant. It's some number, maybe 5, some number that would work out in this context. So it's playing the role of just say this whole 5 you see right here. The variables are matching up with the variable x that's above. And the 5 squared is matching up with the r squared down below. That r squared is also constant. It's just a weird constant in this context. But it means if we go to differentiate, call it, say, dy dr once again in Leibniz notation. Let me scroll down just a touch. It would be no different than what we did up here. I had a coefficient 5, but this one has a coefficient 1. Think of the uppercase r as being just like an x, and you would get a 2r on that very first term. Again, regard that r, where the red dot is, as that same x. If you differentiate something with a variable power 1, whether you call it uppercase r or x, all you keep is the constant term multiplying it. So we carry down plus 2 lowercase r, nothing else from that term, and that's just a constant. Much like the 5 squared, the derivative of lowercase r squared goes to 0, and we get nothing out of that. So we have 2 major results. dy dr for v squared r is just v squared, and dy dr for this entire term, r plus r power 2 expanded into that, gives us 2r plus 2 lowercase r. We'll substitute them back into the original problem up here. But to me, this is the hardest part of the whole process. It's not the quotient rule. It's just navigating those 2 derivatives where the stars are. Any questions on getting through either one of those? Okay, let's plug them back in. The rate of change of power with respect to the only variable in the problem, the resistance, is going to be equal to, first right here, derivative of v squared times uppercase R came out as nothing but v squared right in this spot. So we get v squared here. On this line, we're just copying r plus lowercase r to power 2. Copy further all the way to here, v squared times r. And this derivative, after we expand it into this form, came out as 2r plus 2 lowercase r. You know, let's simplify that one little bit further. That's the same as 2 r plus lowercase r. I think that's easier to put in. So let's go times 2 r plus lowercase r. So we did it, folks. That's the entire numerator. This is really tricky. Again, this is stuff we'll return to in chapter 4. So this is just kind of an early look on what these kind of derivatives look like in applied settings. The denominator is not too bad. A power raised to an external power like this, they multiply together. So this turns into r plus lowercase r to power 4. And this simplifies a little bit further, but any questions to this stage? Okay, this is the end of the calculus step, aside from giving an interpretation of what we have. The last bit is algebra, just to simplify this further. And that's actually going to be a major step in the very next chapter, chapter 4. The big questions in chapter 4 is, what is the value of uppercase R that will maximize power? How do you get to the most amount of power out of this configuration? What does R need to be set to? To answer those kind of questions, we always want to simplify these things as much as possible. And simplifying this is not so bad. Here's how it would go as a shortcut. Notice that R plus R is here, here, and here. That means there's a greatest common factor that could be pulled out. It also means it reduces. So here's one way to visualize it. That cancels into power 1. That's just gone. And this cancels to power 3. So if you're a fan of that kind of logic, that's a great way to write it because it's fast. But it's also extremely confusing to leave on the lecture notes. So here's another way to do that same kind of process. Actually factor out to the greatest common factor, which is r plus lowercase r to power 1. We would get dp dr equals r plus lowercase r. When we factor it out, this exponent drops to power 1. So this is just v squared r plus r minus 2v squared r. It cancels out of here entirely. And in the denominator, still r plus r to power 4. R plus lowercase r to power 4. And now this is a good place to visualize the cancellation. You can cancel from here to here, leaving behind power 3. But either way you do it, you're going to get the same result. This is just the more official way that the author would typically write out this step. Okay, now next step, we're nearly there. We can say dp dr, if you distribute in v squared, would give us v squared r plus v squared lowercase r minus 2v squared uppercase r, divide by r plus lowercase r to power 3. And almost there, we now have like terms. There's v squared r minus 2 copies of v squared r, so that's just negative v squared r for those terms. So we could write our end answer as v squared lowercase r minus v squared r divided by r plus lowercase r to power 3. Finally, we've got it, folks. That's the derivative of the original thing right up here. It's a tough derivative. We looked at two pretty tough derivatives. The other tough derivative that we did, the that interlocked with, say, the product rule, that would not make a very good exam question. That's really two problems in one. But this problem, taking the derivative of something like this, is something that might make it onto, say, exam number 3. This is a skill that we'll return back to later when we're in chapter 4. But the goal was for our notes to try to do an application problem on each section. So this was this section's application problem. A pretty tough one, I would say. We'll finish off this one by giving a practical interpretation. But any last questions or comments, folks, on getting through any one of these steps? Okay, well, let's take a look into what the interpretation should be. We should read the context again just so we can orient ourselves on what the interpretation should be for that particular derivative. It says the power that a battery supplies. When they refer to a power, they're talking about this P right here in the problem. So the power the battery supplies to an apparatus, such as a laptop, depends on the internal resistance of the battery. For a battery of voltage V and internal resistance lowercase r, the total power delivered to an apparatus of resistance R, so your laptop itself has resistance R, not the battery, is this. So that's the power. But once we differentiate it, we can now call this the following. This is the rate of change of the power the battery supplies as the device's resistance R varies. So recall, the voltage was constant, the resistance of the battery itself is constant, but maybe we're imagining we're building a brand new laptop, and we can change as we build this laptop its resistance. And if you change the resistance of the laptop itself, here's how power is going to change. According to this formula, excuse me, I said that incorrectly. This is how the rate of change of the power is going to change, how the power is dispatched to that device. We want to know when is that rate, or excuse me, when is power going to be maximized? That's when this whole derivative is potentially going to 0. So that's going to be the kind of topics that we're going to be looking into chapter 4. But any questions or comments at all, folks, getting through this entire question? Okay, well, we did it, folks. This is a pretty tough section. I would say one of the first genuinely tougher sections that we're getting through in the lecture notes. The chain rule, I would say, is not too bad. It's more of just an interesting pattern that we're going to focus on and refine as we go through the notes in the next section. But if you have any questions while you're solving these problems and the upcoming 3.4 WebAssign problem, don't hesitate to bring them up to class. Hit the Ask My Instructor button. I'll be very happy to help out with them. With our last remaining time, we've got about 11 minutes and some change. Let's look into what's going on with the chain rule section. Starts off with a strange kind of scenario that we're going to look into. This is more just a fast example to think about what is the chain rule really trying to say in essence. So we'll solve this one today. But then next, here's what the chain rule is really all about. The chain rule is going to tell us how to take the derivative of a composite function, an uppercase function f, where f is defined by lowercase f composed with g. In other words, this is the definition of function composition. Uppercase f of x is going to be f composed with g of x. If we want to differentiate that function, it comes together in this really interesting kind of format right here. F prime at g of x multiplied by g prime at x. This multiplication right here is the reason it's called the chain rule. We chain on a new derivative whenever there's a composition, whenever there's a bona fide function g inside of another function f. These are the functions that we really haven't differentiated at all before. And so this will be a new landscape in these notes. But there's a challenge on why does the derivative look like that in the first place? There's a nice proof in the reading if you'd like to take a look at. And there's another challenge of how exactly do you use that? We're going to look into the first challenge of why does this make sense? Why are we multiplying two derivatives together in this kind of way? So the analogy to help us think about the chain rule is this example one. So it's kind of a strange situation, but these are bona fide derivatives. Derivatives are rates of change. And so if we say a car goes twice as fast as a person on a bike, well, when we say fast, we're talking about speed, and that's a rate of change. A car goes twice as fast as a person on a bike could be re-represented as the rate of change of the car with respect to the rate of change of the bike is 2 if you're going twice as fast. Or in other words, for every 2 miles, the car goes, the bike goes 1 mile. So that's what this derivative would say all together. Derivatives are always the rate of change of the thing on top, whether it's a distance of a car, a y variable, power in a function, divide by the rate of change of something in the denominator. So if a car goes twice as fast as a person on a bike, this is really a 2/1, just simplified down to a 2. 2 miles for a car, divide by the 1 mile for the bike. Then there's more drama in this problem. We also have this relationship. A person on bike goes 3 times as fast as a person on foot. We're probably imagining that this car is not going that fast. Maybe this is, say, in a school zone or something like that, or maybe 30 miles per hour zone. If a person on a bike goes 3 times as fast as a person on foot, same as what we did here, we could rewrite that relationship by saying the rate of change for the person on the bike with respect to the person walking on foot is 3. So 3 miles for the person on bike to every 1 mile for the person on foot. So we have 2 relationships, but notice that they're kind of linked. We have the bike here, the bike here. This is a kind of function composition if there's a linkage like that with the bike. Now, here's an intuitive question that you might know the answer to. What would you say the rate of change is if we compare the car to the person on foot? Anyone have any wild guess on what that number should be? Yeah, absolutely, Naomi. It would be 6. The car's going 6 times as fast as the person on foot. So your intuition is absolutely correct. If the car is going twice as fast as the bike, and the bike is going 3 times as fast as the person on foot, that means if we put this all together, that nice fact about this is these rates multiply. The person in car is going 6 times as fast as the person on foot. Here's how we would put it together. Notice these are all derivatives in Leibniz notation. And what we're about to write down is chain rule in Leibniz notation. Here's what it would look like. If we say rate of change of the person on car with respect to the person on foot, this could be re-represented as first take, well, this one. We have to take the rate of change of the person in the car with respect to the person on the bike. that's not the whole answer. We're trying to go and relate the person in the car with the person on foot. So we jumped through the intermediate derivative, relating it to the rate of change from the car to the bike. But our end answer has to be in terms of the person on foot, so we multiply by that derivative. Rate of change of the person on the bike multiplied by the rate of change of the person on foot. Then we could just drop in those numbers. The first one was 2, the last one was 3, so we can get altogether 6 times as fast. But this is literally the chain rule. It's just written out in Leibniz notation. Notice it's kind of tempting to do the following. There's a nice little logic as far as Leibniz notation goes. If you thought of this as a fraction, that cancellation kind of makes sense in the land of fractions. But unfortunately, they're not fractions. We have to always remind ourselves that something like d car over d bike is really the limit as h goes to 0 of f at x plus h minus f of x all over h, where we'd have to make some sense of what is the f function here with respect to the car and the bike. But the major emphasis is it's a true derivative involving a limit. It's not a literal fraction, but it's still kind of a nice analogy that if you thought in terms of literal fractions, that cancellation makes sense. And this is the end result you would get. So that's the chain rule in Leibniz notation. The big takeaway is the derivatives multiply in this kind of way. And that's what's going on the page right over here. If you're doing a function composition, you'll have an inner function, g of x, an outer function, f of x, differentiate this composition. You'll take the derivative of f, that's like the person in the car. You input the g of x function, that's like the person on the bike. Take the derivative of g of x over here. Kind of lost the analogy, but that's the setup so far. The derivatives will multiply together. We copy a function on the inside, multiply by the derivative of that function on the outside. Well, that's the chain rule. Looks like we don't have a lot of time to get through example 2. We took up quite a bit of time on that application problem. But when we return to class on Tuesday next week, this is exactly where we'll be. We'll refresh on how the chain rule works. Look at it in a simple scenario where it's more about just function values, and then start working out to the bigger questions like example 3. The big application to this one will be biology, looking into how fast does blood flow as it relates to a dilating blood vessel, like on this diagram here. But any questions at all, folks, before we call it a night today? Okay, well, have a great weekend, everyone. We'll start off fresh when we come back on Tuesday and get through the chain rule notes. It won't be too bad. I think the last section in many ways is a bit more intense. And the good news is once we finalize this, this is essentially, except for dealing with logarithms, the last big rule as far as derivatives go. So we're getting over the hump once we finish the chain rule section. But have a great weekend, folks. We'll be back to it next week. Thanks. Have a good one.